we are still looking at aircraft response to inputs, and my inputs are atmospheric inputs, right. The last class we looked at the plunging motion of right. We took a sharp edged gust in front of the aircraft. So, this gust was called sharp edged gust. Right. It is like a step input to the aircraft, and we found the response in time as this, right, but this tau is the time constant of the motion, and it is depending upon the equilibrium speed and the derivative z alpha, right. So, now let us try to write this down in terms of aircraft other parameters. Cz alpha q s over m, right, and this Cz alpha is nothing but minus of Cl alpha. The way we define the axis, z is in the downward direction and left is in the upward direction. So, what we get is m u naught over Cl alpha half rho u naught squared into S, and this is equal to 2 into W over S, which is the wing loading, over Cl alpha rho u naught into G. The response is going to depend upon what is the initial condition, right. Initial condition, as in you are trying to find out what is the acceleration at time t equal to 0, right. We are trying to plot this delta W of t as a function of time. So, we need the slope at time t equal to 0, and that slope is nothing but the acceleration. This is the slope of the response at time t equal to 0, right, which is also the acceleration, right. So, let us try to get some numbers for two different aircraft. This is a solved example problem in Nelson. Nelson's book. The units are here feet per second, feet squared, shear alpha is per radian, weight is in pounds, and the aircraft are two different aircraft. One is general aviation small airplane, and the other one is jet transport. Weights are 2750 pounds for the general aviation aircraft and 126,000 pounds for the jet transport. Speeds here are different. One case is 125, the other case is 225 feet per second, and the wing platform area in the first case is 184 square feet and the other case is 2000 square feet. CL alpha is 4.44 for general aviation aircraft and 4.52 for jet transport. Okay. So, what we are interested in finding out is what is the response actually in the two cases, right. So, we need to find out what the time constant is. Now, everything you know here from the data that is given there. Okay. So, aircraft A and B, so you know everything from here, right. So, you can find out what the time constant is. In one case it is 0.7 seconds, the other one is 1.61 seconds. Okay. You also need to find out what is the acceleration at time t equal to 0, right. That is the maximum acceleration that you have, and it is going to take you to the steady state, right. When t approaches infinity, delta w, value of delta w is going to be a constant, right, and that is depending upon the amplitude of the gust. So, clearly whatever amplitude of the gust may be, the acceleration at time t equal to 0 is inversely proportional to this time constant, right. So, time constant for the general aviation airplane is lower, right. So, this slope or the acceleration is larger, isn't it? This is for the general aviation airplane A, and for the airplane B, this is the response. Okay, now we will also discuss about other profiles, right. You can have different wind profiles of this vertical gust, and they could be periodic, or arbitrary, right. So, you can take W g to have a form which is this A g into sin omega t. Any other periodic function also, you know how to write them as a sum of various frequencies using Fourier series. So, if you have a signal which is looking like this, that also you can write as sum of harmonic series, or maybe right. But of course, you are not going to see such profiles, right. Wind can have any arbitrary profile and can look completely different from what you are seeing there. So, it could be something like this, right. But still deterministic, right. There is a deterministic profile. We know what is the amplitude at any particular time, right. So, these are non-periodic profiles. What about aperiodic profile? You could have periodic functions when time period is large is going to infinity, right. So, the profile may be repeating itself after a very long time, right, and that can fall into this category, right, a periodic profile. Okay, so we will not talk about these. We know how to find solution for this case, right. If I know W t as a function of time, some function, then I am still able to find the solution, right. Here you have to do something else, okay, and that is not what we are going to talk about. We will look at simpler cases. So, well, look at first aircraft response to sinusoidal gust. we are still looking at plunging motion. So, equation of motion is not going to change. This W g of t is now right. So, let us look at how this profile looks like. Right. This frequency is 2 pi over the time period. You can use Laplace technique to find solution for this also, but here is much simpler. You can also write down the solution directly, and that is something like this. Right. Let us try to plug this general form of solution in this equation. What you get is now collect terms common to cos omega t and sin omega t from both sides, and what you have is tau a omega into cos phi minus a sin phi, that comes from these two terms, and there is no term appearing on the right hand side which is having the fact. sin cos omega t, and corresponding to the sin omega t term this gives me the time lag in response, right, which is coming here, right. Now, A is the amplitude of the response. Let us write down A in terms of the parameters that are known, right. Time constant and omega, the frequency of the gust profile, these are the known parameters, and I want to look at the response in terms of those parameters. So, what A is? A is AZ over right. So, that your response is this. Right. So, there is a time lag involved here, which depends upon the time constant and the frequency of the gust profile, right, and even the amplitude depends upon these two parameters, right. So, when this parameter is small, right, when this parameter is small, what is happening? This is very small, right, this is also small. So, lag is small and the amplitude is almost same as the amplitude of the gust, right. It is very close. This is the time lag. Right, so closely following the amplitude of the gust profile with a small time lag. Look at what happens when this is large. Okay. When this is large, the amplitude is going to depend upon the magnitude of this, right. It is going to be small, it is almost flattened, no? And having large lag in time, right. Okay, let's say this omega is fixed and we have control over this time constant, right. Time constant is what we have control over. Time constant is related directly to the wing loading, isn't it. So, if you go by that argument, then this quantity is going to be large for airplanes having large wing loading, right, and the amplitude of response is going to be flattened, right? Less amplitude as compared to the wind profile. This is a very simplistic view. Okay, this is not what is going to be an actual case, right. An actual case, you can see all kind of winds. You can also have what is called wind shear. So, wind shear so I am plotting here one profile. Shear is having a gradient, right, with respect to the distance, right. So, if you want to look at one such profile, let us say we are looking at UG and is with respect to let us say height, right. So, this is how the horizontal wind is changing with height. Now, how will you deal with such cases? So, UG is somewhat like this function where h is being measured from the ground. Now, how do you include this part in the aircraft equations of motion if you want to see the effect of this on the aircraft behavior? So, let us write down the equation of perturbed motions in longitudinal case. So, this is our original A matrix in the longitudinal motion. And we have seen how we can include the gust. So, I am dropping here the control inputs, looking directly at the gust input. Right. So, somehow there this delta H has to appear, otherwise you are not going to be able to include that part in the A matrix. Right. Anything which goes into the A matrix is going to change the dynamic behavior. Right. So, let us try to. So, we are looking at a problem when aircraft is on an approach to land, right, and then this gust is encountered, this wind shear, not really gust, this wind shear profile is encountered. Right. So, it is coming to the altitude is going to go down, right. So, we can write the linearized change in altitude as this. So, you include this equation also in this model, right, because now is this set of equation is coupled with this equation. Why is that? Because you have these two terms appearing here now, right, delta alpha and delta theta. So, you can do you can either write this delta W dot in terms of delta alpha dot, or you can do this. So, let us try to include this gust or the wind shear through this equation, try to take that into the same matrix, and then we can look at the eigenvalues. Right. So, U j is du over dh into this delta h, right, that is how we have defined this wind shear. right. What is it going to change? Now you have one more equation, right. So you are expecting one more eigenvalue. Okay. Earlier we had two pairs of eigenvalues for this A longitudinal, and both were again a pair of complex conjugate eigenvalues, right, corresponding to the short period and the Fugite mode, isn't it? Now you are going to see another eigenvalue which is non-oscillatory. It is going to be a real eigenvalue. So now eigenvalues of this matrix are two pairs of complex conjugate eigenvalues and one real means non-oscillatory. So we have sort of understood that change in u is not going to affect the short period motion, right, and that can be seen here also. When you solve this set of equations, it is not going to have much of effect on the short period motion. Okay. The Fugite is different. Okay. Let us so this wind shear is not having or having negligible effect on the short period mode. But it will have an effect on the Fugite motion, and if you want to plot how Fugite mode eigenvalues are moving in the complex plane when you change this gradient, then what you get is so here I am plotting the Fugite mode eigenvalues. So we are starting at this point when du over dh is 0. When you start changing this gradient, the pairs, this pair of eigenvalues will start moving, and it becomes real at this point, and you want to know what is the magnitude of the gradient at this point. It is lying on the imaginary axis, 0.186 per second, right, and this is for airplane B. It is likely that the Fugite mode of this aircraft will become unstable when you have this gradient having large value, and you do not want this to happen, right. When you are close to the ground and you are on an approach to land, right, you do not want this to happen. So this is for the aircraft which has higher CL alpha and higher wing loading, right. For aircraft A, which has lower CL alpha and also lower wing loading, the profile looks something like this. This is example problem 6.2 in Nelson's book. Right. So now we will stop at this point as far as this course is concerned.